Uh, cool, yeah, thanks for hitting record, Mickey. So far, we've spent most of our time, well, at least last week, in Fusion. And a part of this class is learning how to design for 3D printing and hopefully doing some 3D printing as well. Not, you guys won't be doing 3D printing, but I will be printing parts that you design. So on that note, that's kind of what we're going to focus on today. We'll be a little bit less actually using the CAD interface. We will do a little bit of that, but we're going to go through some presentations, and then I'm going to outline our 2-week, it's a little bit less than 2-week CAD project, okay, which is kind of coupled, it's coupled as a competition as well. So it'll be fun. There's some prizes. We'll get into details there. But to start with, I guess I'll open it up to any like small questions that you guys might have throughout the tutorials. I'll give maybe 5 minutes to that, and then we'll get into a presentation. I will highlight one thing that was asked of me today, and as it pertains to the tutorials. Hi, Dana. I'll get to you in just a second here. So I'm going to share my screen. This is just like a small kind of functional thing within CAD, but you'll notice that most of the tutorials, they line up your cube so that the front face is on your, I believe, your XY plane. And I think that's mixed some folks up. So if you want to, you can rotate around to your XY plane, okay? And then if you right click on the cube, you can go down to set current view as, and then click front, and it switches it to your front. And then you're gonna be kind of mirroring what the tutorials are doing. I personally like to design with the ZX as my front, and that's just because I think of height as a Z coordinate. And so when I'm modeling from the origin, Z would automatically default would be my height of whatever object I'm making. So that's why I choose that. But either way, it's entirely arbitrary, and it really shouldn't matter. So that I just wanted to point that out. I know some people had some questions on that. Go ahead, Dana. It looks like you have a quick question.
So I worked on that. I can't find where I put the paperwork, but the essentially the mechanical drawing of the little thing that we were supposed to make and send back to you. And I couldn't finish it. I just got like boggled by it a little bit. I got like halfway. But do I send that in, or do I just hold on to it till I?
That's a great point. Yeah, if you guys haven't done the lesson 5 challenge yet, which I've received it from just a few of you, that's okay. You can, whenever you get to it, I would say send it to me. And if you're having trouble with it, certainly, I guess what's worked best so far is if you get stuck with something, export the file as a .f3d file and send it to me via email with like a short description of what you're caught up on. And then I can download it and interact with the sketch. And it helps me see more directly what the issue is and how to maybe help you get over that hump. So Dana, in this instance, if you wanna send me what you have so far, and then we'll get you on the right track, and you can keep going with that. Yeah. All right. Any other last questions before we jump in? Does that mean someone else is here?
Oh, I actually have a quick question.
Yeah.
So partly because I was saving versions of the work that I was doing in case I totally mucked it up, which happened, and stepping back through, I found it was easier. I saw there's like 10 file limit in the cloud, and what I'd been doing was to kind of work around that, because I was doing some extra, just trying to work through some things to learn. Is there any functional difference between the export seems to save the files locally and then you can access them that way to get around that limit? Is there any functional difference that will be problematic that way?
There's no functional difference that way. If you're building an assembly, like a multi-component assembly, you might run into some issues then. But if it's like individual part files, no, there's no problem with that. It's just the hassle, I guess, of having to upload and download from your computer. But that's a great workaround for the 10 document limit with the free version of Fusion.
Okay, thanks.
To download and store it locally. Cool. All right. Let's go ahead and jump into it. Like I said, we're going to talk about, today's going to be focusing on 3D printing. Yeah. Oh, Bill, that's a hand clap or a hand raise? Sorry, I'm going to ask you to unmute. Do you see that? Bill, it looks like you're muted. Go ahead and unmute and then say what you want to say.
Get the hang of this. I was going to say another option on those 10 limit on the file is to convert them from editable over to read only.
Yeah, that's a good.
You can have a pile of read onlys, and just when you want to work on them, you just convert them. You bring it up and it'll say it's only read only. Do you want to convert it? And you say, yeah, there you go.
Yeah, thank you, Bill, for highlighting that. And Brian, you can probably even see it on my screen here. Right now, I can open up and edit like this small cube and this wine glass because it's editable. And I can click on this and click read only. And that would give me one more spot. I have now 9 out of 10 spots available for editing something else that's read only. So I can go in and click editable. So yeah, Bill, that's a good point. You can.
I've actually made all of mine read only, and I just convert them when I need to work on them. So
yeah, you can store.
Yeah,
you can store many more than 10. I don't even know if there is a cloud limit. I'd imagine there is at some point, but it's a lot. So anyway, yeah, Bill, but good point. Cool. All right. Design for manufacturing. Let's pull this up. I'm still getting used to Prezi. Let me get to the very beginning. All right. Should be at the beginning. So design for manufacturing is also, we like our acronyms in engineering, is referred to as DFM. So what does it mean to design for manufacturing? It means to create parts, components, products for the ease of manufacturing, right? With an end goal of making a better product at a lower cost. It also means to design with the consideration or considering the advantages, disadvantages, and limitations of a very specific manufacturing process. Cool. I feel like that's pretty self-explanatory. Does anybody have any questions on that up front? So we mentioned our CAD workflow a few weeks back, and let's get some responses in our chat, or you can raise your hand and say it yourself. But where do you think in our CAD workflow that DFM should be addressed? Number 1, 2, 3, or 4. Now I got to find where the chat even is when I'm screen sharing. Oh, it's probably over here. Mason says number 1. All the steps from Mickey. Sam, number 2. Dan, number 1. Number 3. Cool. Mickey, I like your answer, Mickey. All the steps. I mean, that is the nature of it. I guess, let's see. Let me scroll back here. I would say primarily it's going to be steps number 1 and number 2. And so for the reason, or I guess to explain that in better detail, once you've have a good understanding of the concept in your head, maybe you've sketched it out. But before you go into CAD and start designing, you want to be, your wheels should already be turning as to how you can manipulate it and design it in the CAD interface so that it's best produced in the process that you're going to be making it, right? If you're welding something versus CNC machining versus die casting, right? Each of those processes are vastly different. And they have their own limitations and advantages based off of those specific processes. So we want to design to optimize the final product. So from concept to CAD model, you're kind of thinking about it, right? You're thinking about, okay, how is this going to be made? How's it going to fit together? What are the limitations? Once you've created your model, and then you go into analysis, right? That's when you're really going to start fine tuning and nitpicking the design. And we'll talk about how you can do that specific to 3D printing in a little bit. Both, Dana and Mickey, you guys mentioned later on in the process, and I would agree with that as well. I mean, you want to be thinking about it every step of the way and further refining your design all the way up through manufacturing. Even after manufacturing, you should, do an analysis of how it worked, how could it be improved if you were to do later revisions, so on and so forth. So even in steps 3 and 4, you're right, but I would say predominantly it's going to be steps 1 and 2 here. So, there's hundreds of different manufacturing processes, all vastly different depending on the material that you want, the application that it's going to be used for. And we're narrowing that focus to like maybe 1% of manufacturing, and that's additive manufacturing, okay? And additive manufacturing, or AM or ALM, is the industrial production name for 3D printing, okay? It is a computer-controlled process that creates 3-dimensional objects by depositing materials, and it's usually layer by layer. So even within this 1% of manufacturing processes, right, and it's called additive manufacturing, we have, and this isn't an exhaustive list, we have 6 to 8 different types of AM. And each of those types, you have to consider different limitations and different advantages because they're different processes, as you're designing your part. So we're going to narrow it down from that 1% down to like 0.0005% of the manufacturing processes available to us. And we're going to focus on fused filament manufacturing, or FFM, okay? And that's a fancy word for the type of printing that most of you are probably familiar with. And that's your desktop 3D printer that melts plastic and creates layer by layer these plastic layers to create an overall object. I'm going to go ahead and we're going to start this video. And I think I can share sound. I don't know that there's much. I think there is some description in here, but we're going to watch just a short video on FFM that does a pretty good job of describing its process.
Fused deposition modeling, or FDM, is a layer additive manufacturing process that uses production-grade thermoplastic materials to produce both prototype and end-use parts. This technology is known to accurately produce feature details and has an excellent strength-to-weight ratio. FDM is ideal for concept models, functional prototypes, manufacturing aids, and low-volume end-use parts. The FDM process begins by slicing 3D CAD data into layers. The data is then transferred to a machine, which constructs the part layer by layer upon a build platform. Thin thread-like spools of thermoplastic and support material are used to create each cross-section of the part. Similar to a hot melt glue gun, uncoiled material is slowly extruded through dual heated nozzles. The extrusion nozzles precisely lay down both support and thermoplastic material upon the preceding layers. The extrusion nozzle continues to move in a horizontal XY plane while the build platform moves down, building the part layer by layer. The finished part is removed from the build platform and cleaned of its support material. Raw FDM parts have visible layer lines. However, service providers such as Solid Concepts offer multiple finishing options to create smooth, even surface parts, including hand sanding, assembly, and cosmetic paint. Since FDM parts are constructed with production-grade thermoplastics, including ABS, polycarbonate, and Ultem, they are both functional and durable. FDM is utilized in a number of industries, including aerospace, automotive, industrial, commercial, and medical.
All right, and they refer to it as FDM, FFM. It's the same process. Do we have any questions so far?
So do you use that at work, Brett?
We do, yeah. We have a Raise 3D Pro 2, which is this style of 3D printer. We also have stereolithography as well, which is an additive manufacturing, but it's done quite differently. But we use it on a weekly basis, I would say. Go ahead, Dan.
Yeah, I was curious about the support structures that it adds. Is that something that's just inherent to the software that's used to actual 3D print for some of these printers, or is that also designed in CAD or something?
That's a really good question. I'll probably answer that question in the next slide, but I'm glad you brought it up so that I don't forget to hit that. Well, I can hit it now, and then I'll hit it again in a second. The support structures are done in Slicer software. Okay, so it's not done in CAD. So if you're designing a part, you don't have to design things that you don't have to design the supports that support overhang angles, which we'll cover in a little bit. Cool. There we go. So I know some of you are interested in purchasing a 3D printer and using it. And while that's not like the main focus of the class, I did just briefly want to highlight the workflow for 3D printing so you can have some familiarity. I think it also helps even from a design standpoint as we're thinking of DFM. So I will run through that real quick. So you guys are going to design something in CAD, and what you'll ultimately end up with is a part or an assembly of parts, and that's going to be an F3D, not FD3, sorry, an F3D file. You're going to export that file as an STL, and STL stands for stereolithography, and it's just how the data is stored that makes those two different. And there are, I think, 7 different universal CAD files that can be downloaded and interpreted from pretty much all CAD software. And an STL is one of the most popular of that 7, if that makes sense. There's step files, which are also pretty widely used. And then from there, you kind of branch out, and there are files that aren't used as often, but are still considered universal. An F3D file is not universal. It's specific to Fusion and how Fusion both stores data and interprets it and manipulates it within the software. So an F3D file is not universal. So for printing, the first step is to convert your part into an STL file, okay? And then you're gonna open that up in a slicer software, which is specific to 3D printing. And so this gets at what Dan just asked, and that is in this environment, and I'll show you some screenshots of slicer software in a second. This is where you dive into things like nozzle temperature, nozzle speed, your print speed, your flow rates, and that's a function of the material you're trying to print. If you're printing nylon, you're going to print with a nozzle temperature much higher than if you're printing with, say, PLA or ABS. So a lot of it's material dependent. A lot of it's dependent on the geometry you're trying to print, so on and so forth. So it's in the slicer software that you determine how the printer is going to print the file that you want to create. Once you've gone through all those parameters, and depending on the printer and the software, that can be, 50 parameters, or it could be 200 or more. But once you've done all of that, you're going to convert your STL file into something else and save it as a G-code file. Okay. And G-code is what the printer reads, and that's how it operates. So it sends the file itself, it reads the file, and it's telling motors to move, and it's telling the heaters when to heat up and how fast to heat up, so so on and so forth. So you save the slicer print file in G-code, and then you take it generally with a USB key. Some printers are Wi-Fi enabled, or you can hook up with Ethernet and send it directly to the printer. But most often you're going to save it onto a USB key, plug that into your printer, and then essentially hit go. There's a lot of hardware things to think about as well in terms of maintenance and keeping the printer up so that it prints well. But again, that's kind of outside of the scope of this class. Maybe in the future, if there's enough interest, we could do a whole class on, focusing more on 3D printing. But does anybody have any questions, I guess, generally about this workflow? Yeah, Bill. You're muted. You're muted.
I've run across something called GRBL or something like that. Does that have anything to do with this cycle here?
GRBL, it may. That's not something that I have heard of. I guess what's the context? Is it a type of file? Is it code that it?
I'm not really sure. It had something to do with programming an Arduino Uno board to drive stepper motors.
Sure.
And it might be that it just goes in there, but I've been trying to track what you've outlined here as a process, and that was somewhere in there. But I think it might have been just getting that board ready to accept G-code, maybe. I don't know.
Did you say GRBL?
Yes.
Okay, I will look it up and let you know. It could be a specific type of code to a specific reader. I would have to look at that to answer.
Okay. Thank you.
Yeah, Dana.
If you guys are using PLA, what do you use? Do you do isn't there like an acetone, kind of like a bath or a wash, like things to to soften up the lines in order to pre-sanding and painting?
That's a great question. Acetone doesn't work with PLA, but it works really well with ABS. So ABS does melt, or I don't know if melt is, it's aqueous in acetone. So that's a great, ABS is a great way to print, or it's a great plastic to print with if you want a really nice surface finish. PLA tends to be stiffer and stronger. Good question. So, I mean, just to give you guys a reference point, this is the slicer software that I use. It's called Idea Maker. And so this is where we pull in the STL file, and this is what it looks like in the slicer environment. We can analyze things like the layer to layer print. So this is a particular layer of the print, and each color, it represents a different, it's all the same filament or the same material, but it's a different part of the print. So the yellow part here is referred to as infill structure. That's what provides the strength or rigidity within a part. You have the green and red here, which is the outer wall. So it's going to make the kind of the outside of the part that you're looking at. And then you have this kind of teal blue, and that is support structure, what Dan was asking about earlier. So somewhere above this particular plane, this material is going to have to bridge and meet this material, but it needs something to build up onto, right? You couldn't just span this whole thing without the filament drooping or not attaching. And so this support material is going to give it, well, support as it bridges this. And then you can peel this accordion layer away. So you're left with a hollow part here, and supported material that spans from here to here further up in the part. Let's see. I know it was brief and there's a lot more we could touch on here, but I guess I'll open it up again to any last questions about how, say, I'm going to be printing your guys' parts that you design in the next couple weeks. No? All right. All right, so getting into the details of designing for fused filament or fused deposition manufacturing. Okay, we're gonna cover 8 things. Again, this isn't exhaustive, but these are gonna be guidelines for you to design your parts with. And the first we're gonna look at is overhang angle. Okay, so this is defined as geometric shapes that hang out or extend outwards beyond the previous layer. Okay, so if you're looking here, this is a cross section of the filament building up on itself, and this layer is going to be supported by this layer if you're at 90 degrees or if you're at vertical. But as you start to hang out, you have less surface for each layer to fuse together with, and therefore less support. And so if this angle is less than 45, or I guess if your overhang angle is greater than 45 degrees, that's good. You want it to be more vertical than horizontal. The more horizontal you get, and this is a great representation here. This is 20 degrees off the horizontal, and you can see that because there was a lack of support material underneath it, or the overhang angle was 20 degrees, it could not build up a sufficient wall to create a nice profile. As you move up in degrees, sorry, I didn't realize this was well see-through, so the lettering is kind of confusing. But as we move up 25 degrees, 30 degrees, 35 degrees, you can see that wall, there's more of it left over because it had more support material beneath it to build on. So that's something we need to consider when we design our parts for 3D printing. Okay, print orientation. All right, it's defined as the face of your part that is adhered to the bed. And the guidelines here is you want to orient your object so that there is no overhang or there's minimal or there's minimal bridging as the part is printed. Okay, so if we look at this table here, you do not want to print like this, or it's less efficient to print like this because first of all, you're going to have to print a ton of support material underneath this table. And the surface finish on the bottom is not going to be very nice, simply because it's built off of support material. If you were to flip the table over and print it, this is the print bed here. If you were to print the table upside down, all surfaces would be supported as it's printed, and you get a much better product. And this is something to think about even as you're designing, right? Like which side or which face should be on the print bed. Larger base surfaces allow for better adhesion and less risk of print failure. Okay, that's another reason to print this table upside down. If you're trying to support the whole thing off of these 4 small areas or points, this whole print could shift on the bed as the nozzle comes across. So you're going to be a lot safer to flip this guy over and print it upside down. And real quick, I will export this in addition to sending the recording to you guys. I will export this presentation in PDF format so that you can have access to these guidelines. Wall thickness. If a part is hollow, the width dimension of the side walls, all right, that comprise the outside of the part. So the guideline here is that the minimum wall thickness be 1.5 millimeters, and you're going to increase that thickness for larger spans and or taller walls. Okay, that's I think pretty intuitive there. You don't want too thin of a wall if you're making a really tall or large vase or something like that. That 1.5 millimeters is driven, it's a function of both your nozzle diameter and the motors that are controlling the nozzle, but then also the filament that you're printing as well. All right, resolution and smallest feature size. So we're going to be printing on the Creator Pro 2, which I have a few of them right behind me. And the layer resolution on these is between 0.1 and 0.4, and I believe that's controllable. So that's spec'd as like the Z motor or the Z axis. The print resolution is plus or minus 0.2 millimeters. This translates or can be applied to the smallest feature size. And so in the Z axis, and this is ballpark, this is kind of a guideline, it's not a hard rule, but you will see that your part is impacted if you go smaller, let's say smaller than this parameter here. So in the Z axis, if you go smaller than 0.5 millimeters, you're kind of at the limitation of what the printer can discern, if you will. In the X and Y axis, I would say 1 millimeter to get a really crisp part. And again, these numbers are ballpark. A lot of what drives what's capable with a printer is also the person operating the printer and their familiarity with the motors and the nozzles and the hardware. And so these printers I've never actually printed on. And so I'm trying to be conservative with these guidelines. If I'd worked a lot with these, I might make the smallest feature size smaller. If I was confident we could reach that spec. But at any rate, okay, bed removal. I mentioned that large areas are better, and they are for adhesion, but your adhesion can sometimes be too good. So getting it up off the bed can be challenging. These beds on these printers are rigid, so they don't flex. Some 3D printers, they come with a flexible bed, which is really nice. So you can kind of bend your part off of the bed. But in this case, on all 3D printed parts on the face that will sit on the bed, I would recommend putting a 1 to 2 millimeter 45-degree chamfer. Okay, that would allow me to get underneath with, say, like a spatula and pry a little bit and pry it off the bed pretty cleanly. Size or build volume. This is the maximum build volume that this printer is capable of. There are many printers on the market with smaller build volumes, and there's many that can go much, much larger. So that's just a function of the printer, and this is what we will be working with. I would say, to be conservative in your design, I would give like a 10 to 20 millimeter buffer on either side of your part. So this is the build volume that they say. If we added a 20 millimeter buffer, this, the width would be 128, 207, and 140, just to be safe. We're jumping right through it. So if you guys have questions, just shout them out. And Mickey, oh, let's see. You guys are, I'm not good at checking the chat. What constitutes tall? From Dan. In reference to what, Dan?
Oh, sorry, I was just when you were talking about the 1.5 millimeter wall thickness. So I think you answered it with the build volume.
Okay, sounds good. I didn't see that, Mickey, thanks. I didn't see that there was a couple hands raised. I only see like the first 4 people. There we go. Awesome. Bill, let's start with you. You're muted, Bill.
You mentioned a chamfer on the bottom of a part.
I did.
How do you get rid of that on the part later? I mean, you have to grind it off or what?
I mean, if you wanted to factor that in, if the chamfer was not like if that doesn't work within the function of your part, then yeah, you would have to build that in and then remove it later.
Okay.
Or you can not use it. You don't have to put the chamfer in, but then you run the risk of, say, breaking your part as it comes off the bed. And the chamfer only applies to parts with really large surface areas that are sticking down on the bed. If it's a small surface area, it'll pop right off, no problem.
Okay. And what about that buffer idea? I didn't understand what you were saying there. What does it mean? There's a tolerance that you have to take into account, or?
Well, yeah. So for example, the bed flatness, let's say the bed is a little bit out of skew. Well, then your nozzle to bed distance is different. And then that means your layer adhesion will be different depending on where the part's at. So your nozzle to bed error, let's call it, will be the largest at the sides. And so if you build in a buffer zone, let's say your build volume is a little bit smaller, you're hedging against that error on the outside.
Okay. Thanks.
And again, if I was, as I become more familiar with these particular printers, that guideline would maybe expand a little bit or loosen a little bit.
Yeah, makes sense.
Dana, go ahead.
I have 2 questions. One, when you're talking about the 45-degree angle, why can't there be support structure under there? I mean, you can put support structure under there and make the base larger, right?
Absolutely. Yeah, it's and again, these aren't rules, these are just guidelines. These are guidelines to make the best quality part with the least amount of work, like post-processing work.
Mhm.
You can do support structure, but anything that requires support structure is going to have a poor or a, let's say, a not as good surface finish.
Mhm.
If that's hidden or if that's acceptable within the function of the part, then we can apply support structure. And I use support structure all the time. So it's not a rule that you can't go less than 45, but it's something to be aware of as you're designing.
I gotcha. And then is there software to take something larger and that can break it up into smaller pieces so that it knows you want a larger piece at the end? You can.
There are some slicers that can do that. You can combine and cut, portions. I don't know of any software that does that directly or really does that well. And that's something that's a good question because that's something I was going to address later today, and how we do that in CAD. So you might design your full part in CAD all at once, but then it's too big, or maybe it doesn't meet some of these criteria. So you would go back and design it in sections so that it's appropriate for 3D printing. And so when we think about our CAD workflow, just to tie it back in, that's the CAD to analysis cyclic pattern. That's step 2. You've made your part, and now you're analyzing it for 3D printing. Cool. All right. The last thing here is bridging. Bridging is the distance the filament can successfully span and create a continuous layer. I think this picture does a great job representing that. So obviously, as you have to span a wider space, the risk of getting these droopy layers or not spanning it at all, the risk increases. So avoid any bridge gaps if possible. The way to possibly do that is to orient your part so there is no bridging. Again, choosing the base intentionally, or I guess the face that sits down on the bed, or at least keep bridging minimal. I shot out roughly less than 10 millimeters, and that's kind of a shot from the hip, having not used these printers. And we might be able to go well beyond that, or maybe less than that. But that might be I guess a starting point for your design. One thing, and this is a more general note on 3D printing. Let's see. Okay, I think we got through all of that. This is a more general note for 3D printing on designing for manufacturing, and that is 3D printing is really useful when it comes to prototyping a design. 3D printing is not great for scaling a product. Okay, so if you're trying to make hundreds of the same thing, 3D printing is pretty darn slow. And that's something to think about also as like as a concept of DFM, is choosing the right process for what you're making. So if you're looking for rapid prototyping or just getting like a first order estimate for like how something will fit together or how it looks, 3D printing is great. Or even custom parts, like one-off custom parts. We make brackets all the time that are really custom and complex to a specific application at Luxel. And 3D printing is great for that, but it's not going to be something that we go to and make 1,000 parts all the same on. It becomes less efficient that way. That doesn't really matter in the scope of this class, but I thought it was at least worth noting, especially for those who are interested in purchasing a printer. That limit for bridging is without supports, correct? Yes, Mickey. So that is without supports. How quickly does the filament dry or harden? That depends on the material, but pretty darn quickly. I would say many materials, nylon, ABS, PE, TG, they actually have to be printed in a heated environment. Okay, so in a closed environment, so that you get proper adhesion between layers. Whereas PLA, for example, you want it to cool as fast as possible, and that's just a function of how the layers bond. But most materials you can take off the print bed right after it's done printing, and without the risk of, like, say, burning your hand or something like that. Does that answer your question, Mason? Yeah, good. Oh, I see you got the video going too. Nice job. Cool. All right. Do we have any more questions on that? That kind of wraps it up. I expect you guys, I expect this will kind of, this will be, you'll design your part, you'll send it to me. I might come back with some revisions and say, hey, your part will turn out better if you do this, this, and this. And then maybe you'll revise it a little bit, give it back to me, and we'll kind of reach a point where, yeah, this can be printed, and it'll be good. So it doesn't have to be bang on at the first iteration. But certainly these are guidelines to think about as you're designing.
Brett, Dana had her hands up.
Oh my gosh, I'm sorry, Dana. You're muted, I think. Let's see. That prompt.
Sorry, I just disappeared for a sec. You just said that some of the materials are printed in an enclosed environment. Does that mean like you have to have a printer that has the enclosed box around it to heat it up, so you can't print those on the ones that are open?
You can't print them as well, right?
Mhm.
Yeah, I mean, you still could, but the layer adhesion, you might be fighting it all the way. So you might get delamination, and delamination is pretty much a failed print. You can't do much about it. And so an enclosed, if you're say trying to spec a 3D printer, which by the way, we're gonna talk next week about all the parameter space by which you can choose and select a printer and how to maybe navigate that. So we'll dive into those details later. But depending on what materials you want to print with will determine what kind of printer you need to purchase.
Thanks.
Yeah. Sorry, the hand raising, it's hard for me to see. So thank you, Mickey, for kind of toggling through the folks here. Any other questions on that? All right. All right, we're almost there. I need to exit out of this. Okay, we're gonna do just some kind of like group examples here for this. And then we're gonna talk about the design competition at the end. So Mickey, I'm gonna kind of rely on you to, if there's hand raises or anything like that, just chime in, or you guys can just blurt out if you want. But this will be kind of a group discussion. I have some examples here for designing for DFM, and I'd like this to kind of be I guess a dialogue between us for what we think is going to be the best way to print this thing. They're pretty simple examples, but what are some things we want to consider if we're looking at our 8 different guidelines here or parameter spaces when we look at this part? Someone want to chime in? Overhang, for example. Would we have overhang in specific orientations if we were to print this, and would we not? Yeah.
Turn it over.
Yeah, turn it 90 degrees so that the hole is up and down,
Okay.
so that the side is on the
Yeah.
the plate.
Sorry.
There, that's it.
Yep, that's right. That's good. That is going to be the best orientation for it. Nice job. You
Yeah.
could potentially print it like this, but why wouldn't we?
Why wouldn't we print it
The
like
hole.
that?
The
Yeah.
whole is clean if you print it like that.
Yeah. Thank you, Dana. So yeah, Bill, you were right. You want to print it like this, and the reason we wouldn't want to print it like this with this edge being on the base is because our overhang angle exceeds our limit right here, and this surface quality isn't going to be as good.
No.
What's another thing, and this might not be as straightforward.
So, didn't you say something about having just a little bit of a just a small 45-degree angle cut so that you could get a spatula under there to be able to pop it off the base?
Great point. Yep. So this,
Or it has it?
yeah, and this may be a small enough part where it's okay not to, but I think rule of thumb, if you can, if in the form and function of this design, if you can tolerate just a small chamfer around the bottom edge, that is going to be a good thing. So you can come around, and I just clicked on modify fillet, except I don't want to fillet, I want a chamfer. Fillet is a rounded edge. Chamfer is a geometric linear angle.
Could you just put the chamfer on one side if there's like one side where you wanted it pretty flat and one side where it doesn't matter so much?
Sorry, go ahead.
Do you need the chamfer on all sides on that bottom, or does it work to just have it on one side so that you have like one spot that you can chisel it up from?
That's a great point. I wouldn't necessarily need it on the perimeter maybe for this thing, but if you're printing like a 6-inch by 6-inch cube, it's nice to get underneath it from multiple angles and to kind of lift it up off the bed. So I guess the answer to that is it depends. But in this case, we'd probably be okay to put it on just maybe this long edge here and this back edge. Cool. One more thing, and this is a little bit convoluted, and if you were to have designed this part, you would already know, but we want to make sure that this thing as a whole is not too small. Or for example, we want to make sure that the circumference of this meets the criteria for our smallest feature size. All right. The radius is 10 millimeters. So it's well outside of our smallest feature size of, I think it was 1 millimeter. And so we're not going to be running the risk of not being able to meet the XY resolution of the printer's motors. So yeah, this part is in the clear.
Mhm. Good.
Okay. This one, I just wanted to throw a curveball, but does it look like we could print this?
How big is it?
Yeah, that's the question I wanted to hear. So it's 0.75 by 0.75 millimeters. And all I was really getting at here is, and this is more if you're to open up a part file that's made by somebody else, it's really important to get an idea of the scale of what you're looking at, because you aren't going to get an idea of that based off of just opening it. You can make this box look as big as you want.
Yeah.
So it's 0.75 by 0.75. That is not going to meet our guideline of 1 by 1 by 1 millimeter. So, or 1 by 0.5, I guess, in the Z. So we'd have to go in and increase our height and width to meet that specification. And that was just I think 0.5 millimeter in the Z was our minimum feature size, and 1 by 1 in our XY. So if we printed with this face or this face on the base, that would probably work. That's a tiny cube.
Brett, if you're just looking at that cube and you didn't know what size it is, would you go up to the inspect icon and pull down a measure? Or is there some place you can click maybe down on the bottom there and find out how big it is?
There might be, there's many ways to do the same task. And the one that I know of, Bill, offhand, is to go to inspect measure, or you can click I anywhere, right? You can click I and then highlight your edge. But it sounds like maybe you know of another place to find that information.
No, I don't. I've come across that before. I've opened up something and looked at it and said, I don't know what size it is. And all of the dimension lines are gone when you're looking at it like this.
Okay.
So
One more thing you could do is go to body, okay? Right
Uh-huh.
click and go to properties, and you should be able to see volume right there,
Oh, volume, okay. Well,
which doesn't, I mean, because it's a cube, it's pretty easy to discern what the edges might be. But if you have a complex geometry and you're looking at volume, that's
Yeah.
not a good indication of your XYZ components.
is there anything you can click on that brings up the original dimensions that you used to constrain the sketch? I mean, that kind of stuff?
I mean, not without, I guess, going into the sketch itself.
Okay,
And
It looks like,
highlight
sorry.
the sketch on and off here. Yeah, go ahead, Mickey.
I was gonna say, it looks like if you look under properties, it looks like there's a bounding box option, which if you click on that, you can see length, width, and height too.
So let's go back to properties. Thank you, Mickey. Bounding box. Center of mass. That's showing the center.
Here, hold on a second. If
You-
you look,
Want to share your screen?
if you pull up properties again, there's a little down arrow to open it up. If you click that,
There it is. Got it. Yep. Great. Does that answer your question, Bill? I think that's a great.
Huh. Yeah, that's good. Okay, good, thanks.
Thank you, Mickey.
So does that show, what if it was a funny shaped object? That's a cube, so it's easy. What if it was
What if it was a wine glass?
yeah,
You're looking at it's still going to create a bounding box that sits
around that?
just outside that. So let's look at,
Okay,
you know what I wish if you clicked on this, if it showed the bounding box, right? That'd be kind of nice. But here it is. And that we know is going to be, I mean, it's going to be on the outside. It would be a box that comes straight up tangent to the outside here and then across the top. All right, if we're looking at this for printing, what would be the few things we want to look at if we already looked at the overall size?
The shell thickness.
Yes, thank you. Awesome. So if we open up shell, it's 1 millimeter. So that's below our minimum of 1.5 millimeters for PLA, or I guess for the printer. And let's just take a look at the height here, which I'll select my top plane and my bottom plane. 75 millimeters, so it's nearly 3 inches. That's fairly tall. And Dan, this is where it gets into kind of more of the guideline territory. There's not a hard set rule for thickness. And really it's just a matter of how well does your printer create, if your layer to layer adhesion is really, really good, you could make thinner parts, but that's more a function of your hardware, your printer hardware. So if I wanted to be absolutely certain that this thing was structurally sound, I might come into shell and make it like 2.5 millimeters and print it that way. And if that's like way too robust, I could print it again and shave the thickness off a little bit.
Brett, it looks like the overhang from the bottom to the middle and from the middle to the top may be close to that 45-degree angle.
Thanks, Bill. Yeah, so that's the other thing we want to check. So if I go into my sketch,
Uh-huh.
all right, we know that at the bottom and at the top, this curve is going to, well, it'll be steep here, but we can check, say for example, this point here by creating a tangent line.
Oh,
So,
yes.
yeah, this tangent constraint, and then I'm going to click inspect like this, and it's 141. So if we do 180 divided by 141, 39 degrees. So you're right. That is just outside our 45-degree margin. So it's a little bit too steep. So you could potentially go in and redesign your sketch. See, this isn't fully defined. If it was, we could, change some of the parameters. But that might be something worth changing because,
Mhm.
because there's only a few points on this curve, and the one that we're most concerned about is at the bottom here. But the rest of it is not. We might be able to print this as is, and so in this particular case, I might throw it on the printer and hit go, and then revise it if I needed to.
Yep.
And if we go back, I just want to hit this real quick. Again, it's not a hard set rule, but we can see that it slowly degrades as we decrease that angle. So at 39 degrees, which is just about here, we're still going to be probably okay, and we could maybe sand the part down to get a better surface finish. So we'll keep it as is, but that was a nice thing to highlight.
Okay.
Mason had a question too.
Yeah, Mason, go ahead.
Hey, so my question is, will a 3D printer understand that it can't do that, or will it try to do that and fail?
Oh, it'll try to do that and fail. The 3D printer's dumb. All right, you give it a set of coordinates, it goes and it does it, and it will. I've had prints that look like a literal rat's nest. When you come into work, and it's been printing for 6 hours, and it's just a heap of wire, pretty much. So that's the result of not designing properly, or maybe just a failure to print and because of the hardware.
Okay, thank you.
Steven, yes.
So would it be possible with the 3D printing to put a fillet around the inside of the base to reinforce the part of the curve that is potentially vulnerable?
Yeah, you could do that. You could. So you're saying you could like round the bottom here.
Mhm.
Yep, that's absolutely something we could do. We could come down here and fillet it. I think it's worth highlighting, if we're gonna fillet that, we want to fillet it before the shell. Okay, if you fillet after the shell, then you're not going to have a uniform wall thickness because you have a hard edge on the inside. Let me just show that real quick. So if I fillet this at like 2 millimeters, it's going to create a rounded edge there, but we still have our sharp edge here because it's done after the shell. So you want to do all your outside filleting. I'm going to delete this before you do the shell command. So I'm going to toggle my timeline down here back, and you can see that it suppresses the shell feature. And then I'm going to, because I'm at this point in my timeline, I'm going to insert that fillet on the bottom edge. We'll do it 5 millimeters. All right. And then I can go back through the shell command, and we'll see that it's rounded on the inside now. So make your outside fillets before you use the shell command. Dan, or did I answer that for you, Stephen, first?
Yes, you did. Thank you.
Go ahead, Dan.
Slightly off topic, but as you talk about like printing multiple iterations of something to see if it works, I know some prints take longer than others, but just as far as like raw material, is it pretty costly to, I mean, do you have just kind of a rough idea of like what it might cost to print something like this, like maybe this vase?
Yeah,
for
I mean,
wine glass?
this vase, we're looking at its properties, or let's look at its volume. Oh, in millimeters cubed, you kidding me? I mean, it's less than $1, and that's what makes 3D printing such a good option for fast, inexpensive, and fast turnaround on development or design, is because it is so cheap and pretty hands off in terms of a manufacturing process.
Okay.
Yeah. Let's see, Brian. Yeah, go ahead.
So like jumping back a couple questions and talking about this this curve off the base being, I think you said about 41 degrees or whatever, and being a little bit out of spec. if this were to be flipped over, and you're printing, it has, well, it at least appears a slightly shallower curve, or if we were to say that it definitely did, as you're to be building up, do you potentially have more tolerance for a steeper curve as something comes to close because it's built on more of its, like if you were going to be like stacking bricks or something, you could get more structure toward the top as the figure closes? Would that work in the same way potentially?
I would intuitively, I think so. So I mean, you're saying, do you have more forgiveness up here in this part of the vase than you do down here? And I would think so. Yeah.
Yeah, and well, and in this example, do you need the solid base? If we were just to flip this 180 degrees, so the print surface is the rim and the solid base is at the top,
Like that.
would, yeah, and if you had a gentler curve at the bottom and a more extreme at the top, oh, but then you have the problem of closing
Yeah.
solid.
So from the perspective that you're discussing the outside angle, yes, I would say that's absolutely correct. But you are right that now we have to put support structure on the inside of this thing. So there's that to consider. But yes, you're right in terms of the curve.
Okay, thanks.
Yeah. Steve, your hand is still raised. I'll take a few more questions and then I want to get to, or have time to cover our project. But do you have any more questions, Stephen?
Nope.
Okay. Anybody else? These are all great questions. Okay. If not, then I'm going to pull up our another quick presentation that's going to kind of highlight our project for the next 2 weeks. Okay. So I'm calling it a competition, but don't fret. I think it's going to be a lot of fun, and it's really just a project with prizes. So if you win, that's great. If you don't, it's still fun, and you're going to get a 3D printed part. That's a prize in and of itself. So that will be good. I'm going to start by highlighting the rules and the rubric, okay, and then we're going to cover both the design topics. I picked the topics hoping, first of all, I have 2 instead of just 1, and I made them vague enough that I really hope that everybody can feel involved and like they're making something that they are interested in. All right, so the rules for this is you guys are going to have to fulfill all of the design topic attributes, which we'll cover in a second, okay, for each topic. You're going to export at the end, once you're done designing, you'll export your FD3 files and email them to me. And in that email, you're going to provide a brief description of the design and its function, okay? And again, you guys are going to have access to a PDF version of this presentation, so you don't have to write it down or anything like that. Submissions must be emailed to me by midnight of Sunday, June 13th. And I am big on fairness. So because there's prizes involved, if I get a late submission, I will still 3D print it. It'll still be, a great project, but you won't be considered for the prizes. So please get it into me by midnight, Sunday, June 13th. And that gives you 12 days from right now. Late submissions will not count. Already covered that. 1 submission per design topic per person. So that means you can submit for both design topics. All right. You can design up to 2 things total, but it has to be 1 for each. It can't be like, 2 designs for one of the topics. It has to be 1 per each. Okay. And this is I think this goes without saying, but it must be your design. All right. There's so many open source things where you can go, export somebody else's design, and that there's no way for me to check that, but let's have, just some integrity here and make sure it's your design. I will say that if you guys have questions on how to make it in Fusion, that's completely fair game to send to me and to ask questions, and I can help you get through those hurdles, and it'll still be your design, obviously. So I'm pretty much entirely accessible for those points where you don't know what to do or how to make something in Fusion. All right, the prizes. There's going to be 2 prizes for each design topic, so there'll be a total of 4 prizes. Okay, and for each topic, we're going to award the best design for manufacturability. That's what we just covered today. And then there's going to be one for best use of CAD. All right, and that's where you're sharing and showing your understanding of parametric sketches, the various extrusion tools, so on and so forth. Gift cards, there's a list of places from around the islands, depending on where you're from, whatnot, that we can get gift cards from. If you have something else you're interested in, I'm open to it. I haven't gotten the gift cards yet. Once you win, you can tell me if from this list or maybe from somewhere else that you'd like to get that from. Yes, Mickey, you can. Or I can say it.
That's okay. I just wanted to make sure that I wanted to say that Brett was really generous and doing the offering these gift cards. It's not coming from the EDC at all. I want to make sure that he's really gone the extra mile and that he gets the credit for that.
I guess since Mickey's saying that, I will say I am all for giving back to our communities and promoting local businesses. So I'm happy to do this, and I think it provides a fun incentive to really practice and work with CAD. So, yeah, thanks, Mickey.
Good idea.
Yeah, thank you. Yeah, thanks you for doing that, Brett. I'm afraid we didn't even think of that on our EDC end. So
no, you're totally fine. I'm happy to do it. I'm excited to do that. Okay, so that's the rules. Let me get through a little bit more here, and then if there are questions at the end, we can cover that. All right, the rubric. I have 1 and maybe 2 coworkers that are going to review these with me. And we're obviously going to try and be as fair as we can. So I've made a rubric that we're going to grade and scale off of, that will give us a pretty concrete scores on each design, that are going to be unbiased as much as possible. Let's see. For best design for manufacturability, okay, that's one of the prizes. We're going to be grading on a scale of 1 to 5, okay, in all of these following categories. All right, so the understanding of CAD, the complexity of the part, which I will say, you guys have 12 days to design a part, so it doesn't have to be, sky's the limit, obviously, but don't be overwhelmed that you have to create the human brain in CAD or something like that. But complexity will factor into this. The 8 concepts of DFM that we covered will obviously, that'll be kind of the core of and weighted more heavily than these other things. And then the novelty and creativity. So how novel is this idea and this design, and how creative were you in this concept? For the best use of CAD, okay, this is the other award for both topics. You're also going to be getting a score of 1 through 5 in these categories. So your design history and design flow, okay? There are several ways to end at the same product, but there are ways to do it cleaner, nicer, and say more concise than others. So we're going to be reviewing the design history. That's that little bar at the bottom of, Fusion 360. Again, the complexity of the parts and the features, the number of extrusion tools, modify tools, sketch tools, planes that you use. That's all going to be counted or accounted for in this. The use of 2D and 3D parametrics. We'll take a look at your sketches as well and kind of grade on the basis of how easy will it be to go in and edit this design or change this design later on without affecting the overall function of it. Of course, fully defined sketches, we've covered that a lot, I think, up to this point. And also novelty and creativity will be a part of this award as well. Because we like to make new things. That's what designing is all about. All right, what you've all been waiting for, the topics. What are they? Design something for your garden. Okay, it can be anything. And these are loose, you guys. As long as in your description you give some connection to your garden or to plants or whatever, then chances are I'm gonna accept it. If you have a question about a design that you're like, oh, does this count or whatever, which I'm gonna accept those things. But shoot me an email. Shoot me an email before you really dive into it, and I'll say, yeah, that works. Run with it. The attributes that have to be hit: less than 7 3D printed components. Okay, and I'm going to give you one example, and it's not to like, I kind of fumbled back and forth with like, should I show them examples or just let you guys go and run with it? But I'll show you what I made for the garden topic, and just to give you an idea of I don't know what we're looking for. But less than 7 3D printed components for the overall assembly. Each 3D printed part, of course, less than our build volume. I built in a little buffer here. It looks like 10 millimeters. If you want to be safe, I would maybe do 20. Obviously designed for 3D printing, and it must have a defined purpose in the garden or related to plants and or gardening. And the design can have other materials or objects that are used other than 3D printed parts. So if you need hardware like nuts, bolts, things like that for it to be assembled, totally fine. Okay, it's however you want it to come together, that's up to you. If you need to glue things together, if someone's making something that wants to be that needs to be waterproofed, 3D printing isn't necessarily going to be waterproof. So if you're making like a vase or something, it may have to be dip coated in like an epoxy or something like that afterwards. That'll be up to you to do. But you can obviously use other objects in the design.
So Brett, what kind of materials are going to be printed in?
That's a great question. I didn't have it listed on here, and I will list it before this PDF gets sent to you. It's all PLA. Okay, it's simpler that way. At least with these printers. So that's what we're going to be confined to. Thanks for asking that. Are there any questions about well, let me get through the last one and then I'll open it up for final questions. Design a novel 3D printed tool. Okay. Any tool. I mean, it can be anything. And a tool, and by tool I mean something that has a distinct function. Okay? So that's like sky's the limit. That's a pretty broad umbrella. Again, less than 7 3D printed parts, same build volume. In this case, you must really clearly define the tool's function. Okay, that is something that we are looking for. And you must be able to, in addition to that, clearly highlight the novelty of the design. Okay, what's new about it? What's different? Maybe you're improving something that already exists. You're changing the ergonomic handle on a hammer and tell us why or something like that. But you must be able to clearly highlight the novelty of it. And again, you can use other non 3D printed hardware. or materials to finish this assembly. So I guess what that means, you know, if you're, let's say you're designing like a hammer, for example, you're just going and you just want to design and 3D print the handle, you can specify in your CAD that the actual hammer portion of it or the head portion of it will be made of metal, and that'll you know come later. So you can specify that in your CAD assembly what will be 3D printed, what won't. All right. So before I show you my what I kind of threw together for the garden, just to kind of get your creative juices flowing, why don't I answer questions if you have any? Sounds like it was pretty clear. All right. Looks like you guys just want to get started.
Yeah. Brett?
Yeah.
You put out 2 topics there. If
Yeah.
the person just wants to choose one of them and submit one design, is that fulfilling this requirement, or should we all
Yep.
try to do 2?
No, one is fine. One is totally fine.
Okay.
And if you wanted to say 3D print something that isn't covered in either of these topics, but still kind of follows those attributes, you won't be a part of the prize selection, but we can print that, and that could be your project. But I think it'll be more fun if we all take at least one of these topics. Yeah.
Yeah.
Thanks, Bill. All right. This is let's see. Yeah, go ahead, Dana.
Question that's not related to what we're talking about, but and maybe you want to talk about it next time. I just don't want to forget to ask you this.
Yes.
I don't know if you know this, but I had this little figure made. I had a bunch of 3D printed figures, but it was so different than the other figures. Do you know if that's like rotocast, or like sometimes some of them had hollow feet and then there was just like white powder that came out of them?
White powder.
Yeah, I just don't know. I can find out what they're made of. I just thought I'd ask you if you knew what they you know.
The white powder came out of like a hole. Yeah, Mickey, go ahead.
I used someplace called Shapeways to print something, and they did use a similar process that made sort of powder in the middle, and I think it was some sort of sintering method that they used.
This is from Shapeways too. Yeah.
Yeah.
It does sound
Okay.
like.
Cool. I will research it. Thanks.
So this is going to get at I also want to show this because it gets at a question Dana asked earlier, and that is that the part as it stands right here, this is a bird feeder, okay? And this would sit in a garden. As it's made right here, it really can't effectively be 3D printed, right? And so the process that I'm going to use for making this bird feeder is I built it as one solid structure in CAD first. And now I'm going to go back and piece it together and figure out how it's going to come together. That's the CAD analysis cyclic pattern that we see in our CAD workflow. So for example, what I'm going to do is I'm going to 3D print the islands. That's Lopez, that's San Juan Island, and Orcas will be over here. I'll show you real quick how I did that. Many of you have seen how to put a canvas on a plane. Okay, so I put San Juan Island right there. And then I zoomed in and made a ton of tiny little lines and connected them up and then extruded it off of this wall. And same for Lopez. And then we have Orcas that'll be done over here. Okay. So what I'm going to do to 3D print this is, first of all, I have the lid, and I'm going to make a new file that's just the lid, and I'm going to design it specifically for 3D printing. I'll probably have to put some support structure in there, that's okay. I'm okay with support structure on the inside of this because we're not going to see it. So the surface finish isn't a huge concern for me. Then for this, then for the column structure here, that'll be the second print. And that's kind of a hollow shaft. I can't really get at it right here, but it's hollow up and through the center here. And that can all be one print. Okay, it'll be a long, tall print with 4 legs, kind of like that table we saw earlier.
Mhm.
Then I'll print the base. And I don't know yet. I might make 4 slots that this thing sits into and somehow fastens to, either with screws or glue. But I'll have to decide how I want to integrate this structure into the base. And then the islands are all going to be their own individual prints. I'm going to have to go in and make sure that I'm not exceeding my limit for smallest feature size on some of these. And if I am, I might round corners. I might take out some of the really small nooks and crannies. And it might be a generally more curved structure of the islands. But I will 3D print each of those, and I plan to glue those or epoxy those onto the wall. Now, there are many other ways to approach this. You could, for example, 3D print each wall separately so that your islands are printed directly onto the wall face, and you don't have to glue it. So this is just how I'm going to do it. I might change it as I look at it closer, but that just gives you an idea of kind of how to start thinking about how do we design in CAD, and then how do we take that next step to making the part designed and for 3D printing. Yeah, go ahead, Bill.
So each of your parts is going to be its own separate file. Is that right?
I will probably do it that way, yes. The other way you could do it is, well, I'm going to make them all as their own separate file, and then
Yes.
I'll pull them into another file where they're all in one as an assembly. And we haven't yet covered how to put more than one object in this environment and constrain them with planes and joints and so on. And that, I believe, is lesson 8 or lesson 9. But up through lesson 5, which you guys have now, I think you have the tools to at least get started. Okay. And then we can piece together assemblies and stuff like that as you go on with the tutorials.
But at this point, if we just make each part a file, that'll get us started.
Absolutely. Yeah, that works great. And you can make the whole thing as one structure to start with and see how it looks. And then yeah, from that, start making individual files of each part.
Okay.
Yeah. Right. Other questions?
Yeah, Brett, do you have some sort of way, if you were to print the islands separate from that main structure, to have like an indication as to where the island would fit in your design? Or is that just kind of like after printing, you have that creative control there?
You're saying, is there ways to register the island on the wall?
Yeah.
Yeah, totally. You could come in and have this inset a little bit, right? So that it marries to it.
Right.
You may run into some issues with, I think if you were to inset the islands in a little bit, you'd probably be okay from a 3D printing perspective. You may have to go in and sand a few edges so that it fits nicely.
Yeah.
But that might be, for one example, how you could locate it.
Right. Yeah. Thank you.
All right, Brian, go ahead. That'll probably be our last question for today, because we're past our time. But go ahead, Brian.
Oh, sure. Just to follow up on the question that was just asked, I didn't see who it was, but could you potentially, if you had the island that the showing face is face down, print like 2 or 4 pins or something that are oriented to the face, and they would snap together and give
Yep.
a specific orientation.
I think that would work really well. Yep.
Yeah.
Yep. Yeah, that's great. If we'll wrap it up there. You guys, I would say to start with, just get it out on paper, sketch it, whatnot, and then you can enter the CAD interface and start designing it from there. Please feel free to email me your part files as you get stuck, and I'm happy to help get you through that. I will say I want to wrap up with one more note. Please keep up the tutorials and try to get through lesson 7. This will help you directly with the project, but I guess that's all I have to say on that note. Cool. I'll stick around for a few more minutes if you guys have questions, but otherwise you're free to go, and we'll see you next Tuesday.
Thank you.
Okay, thanks, Brett.
Thanks, Brett.
Thanks, Brett.
Thanks.